Here we can see all possible numbers that we can write using just 4 bits, starting from 0, which is 0000, till 15, F in hexadecimal number. And now the question is, how can we represent a negative numbers? Because all these numbers are all positive. And if we want to write a negative number, how can we do it using binary numbers? So the first idea, a very naive idea, should be to use some particular symbol or sign to represent minus or plus, which of course is impossible. For example, this is number, this is number 5, and we'd want to add a minus before this number in order to represent the number -5. But in computers and digital electronics, we don't have any special symbol. We only just have bits. So every data should be represented using just 0 and 1. So our next idea could be to use a bit to represent plus or minus. For example, we can decide to use 0, the first bit, the most significant one, to use 0 in the first place to represent a plus sign. So this should be +5. And use 1 to represent a minus sign. So this number should be not D but -5. And here is the table with all the possible combinations, and you can see how it works. These first 8 numbers from 000 to 0111 all begin with 0, and so these are all positive numbers, and these 8 ones are negatives because they all begin with 1. And we have 16 possible combination of 4 bits, because 2 raised to the power 4 makes 16, as always. And in this case, 16 combinations are divided into 7 positive numbers from 1 to 7, 7 negative numbers from -1 to -7, and 2 zeros. You see, we have 2 different representations for number 0. And the first representation is 0000, which is 0, but also this one beginning with 1 is 0. So this is +0, and this should be -0. And I want to show you that the hexadecimal number and the binary numbers remains the same between these 2 tables. The only thing that changes is the representation of in decimal. So, for example, this is always F, this is always 1111, but in this case, this number is 15, and in this case, we consider this number as -7. So first, you notice that if I want to use a bit to represent the sign plus or minus, of course, we have less positive number, because before we had 16 numbers, 15 positive numbers plus 0. In this case, we just have 7 numbers positive, because we used the other combination to represent the negatives one. So we have divided in 2 our binary space in order to accommodate the positive and negative numbers. But I told you there is a problem, because we have 2 different combinations which represent the same number. 000 represent 0 and 100 represent 0 or 2. And this is a problem, first because we are wasting a combination. We are using two numbers to represent the same decimal number, but this is, of course, is not a big problem. And a bigger problem is that with this particular method, using one bit for the sign and the other bit for the number, we have to design two different circuits to make the addition and to make the subtraction. So if we want to add, we need a different circuit, different from the circuit needed to use the negative number. So this is a very uneasy, not useful way to represent negative numbers. And so I want to show you a better hypothesis, a better method, and this one. Here we have a counter. This is a down counter, so it's a counter at 4 bits that counts backwards from F till 0 going down. And you don't have to worry about this circuit, it's not important. You have just to follow my thinking. In this case, we have number +7, of course, 7, and we go back, we go down till 2, 1, and 0. And my question is, now, if we go down again, one number down, which number we will encounter? Of course, the next number should be -1. And we can see that with this counter, the number -1 is represented as 1, 1, 1, so as number F in hexadecimal system. And if you go farther down, the next negative number, which should be -2, is this one, and this one is -3, and so on. Here you can see the result. And this is 0, so this is number 0, and this is number -1, -2, -3, and so on. And you can see that now we have just one 0 value, this one, and then we have 7 positive numbers and 8 negative ones. This is quite strange because there are more negative numbers than the positive ones, and the reason is because all numbers that begins with 0 are positive, so this is 0, but it is considered as a positive number. So in reality, all numbers from 0 to +7 are positive, and these are 8 combinations, and these other 8 combinations are negative numbers. This particular kind of representation is called two's complement. It is very strange in the beginning because one can understand why this number is -1, because it doesn't look like a -1. But I want to show you that this the simplest way, the most natural one to represent negative number using binary system. And first, we have this interesting property that all numbers beginning with 1 are negative and all numbers beginning with 0 are positive. But you don't have to consider the first bit as a sign, because this is not -0 as in the previous signed number representation. This is not a particular bit, it is included in the number. So this is not, for example, -7, because it begins with 1, but we don't have to separate the first bit to the other one. Are all together these 4 bits is -1. So how it works? I show you how it works using this site. I write here a positive number, for example 0011. I am using 4-bit numbers for sake of simplicity, but we could use even 8 bits or more is not a problem. So this is plus 3. And we want to calculate the minus 3, so the 2's complement of plus 3, this is plus 3, and this one is minus 3. How can we pass from, how can we calculate the opposite of a number, given a positive number, for example this one? Which is the method, the procedure to calculate the negative correspondent number. So the method is this one. So this is plus 3. I recognize that this one is a positive number because it begins with 0. And this one is the negative number. 2's complement is 1101, which of course 1101 is minus 3, but the details are here. The method is this one. I know it sounds crazy, but it is not crazy. Trust on me. I take the positive number 001. First thing, I have to invert all values. Swap each 0 with 1 and vice versa. So for example, this is 001, we have to swap all bits, and so 0011 become 1100. This is the first passage. And then we have to add 1, just 1, to the result. So this is our opposite number. We add 1 and the result is 1101. So this is the general way to transform a positive number into a negative one. For example, we can try another simple example. This is plus 1. If I calculate the 2 complements of plus 1 is minus 1, and this minus 1 we know is 1111. But the steps are, I take 0001, sorry, and invert all values, so I obtain this number, and then I add 1 to the result. So the result, which I repeat, is called 2's complement of the first number. The result is 111, and I want to show you an interesting properties of complement, 2 complement number. For example, if we take the number representing minus 5, which is 1011, and so I write here 1011, which is minus 5 in this notation, and if we complement here it, we obtain the number 5. So the operation of 2 complements transform a positive number in the correspondent negative number and transform a negative number in the corresponding positive one. So it is opposite operation, and you can see the details here, which are always the same. Invert all values, add 1 to the result, and obtain the final result. So this is a very interesting property, because if we take a positive number and apply to it 2 complements, we obtain a negative number, but if we repeat the operation of 2's complement another time, we obtain again the first number. So the 2 operations are completely opposite one each other, like multiply to minus 1 in decimal number. If we multiply for minus 1 a positive number, we obtain we have a negative number, and if we repeat the product, we obtain again the first number. And now I want to show you a last very important property of 2 complement binary numbers. And this property is that we can add positive and negative numbers using the normal adder, so we can treat negative numbers like positive one. I show you it by an example. For example, I want to add the number 6, which is plus 6, which is this one, and calculate plus 6 plus minus 2. And of course, the result should be plus 4. I'm using a 4-bit adder here, and here I write plus 6, and here I write minus 2, which is 1110, 1110, and you can see the result is plus 4. So this is here. Here you have a normal adder, 4-bit adder, which we designed in a previous video, and you can see we can use a normal adder to make subtractions because we only need to represent negative numbers with 2's complement notation, and the circuit works in the same way. I want to show you a last example. For example, I want to add minus 8, which is minus 8 should be 1000, and add to minus 8 the number 3 plus 3. So minus 8 plus 3, the result is 101111, which is 1011 is minus 5, which is correct because minus 8 plus 3 plus 3 makes the result minus 3. So you can see with 2 complements number we can represent positive and negative numbers in a quite strange but logical way. And the most important thing is that in this way we can use the same circuits for positive and negative numbers with no difference. We can use the adder for to make addition and subtraction exactly in the same way.